In our previous video, we talked about inverse trigonometric functions. We talked a little bit about inverse functions in general, or inverse relations, and then we looked at what we have to do to a trig function to make it have an inverse, which is a function. Of course, the trig functions really don't have inverses, which are functions, so we have to look at a restricted version. And we looked at the Arccosine function. So in this video, we're going to be looking at the Arccosine function. Very similar to the Arcsine function. So we can start by looking at a graph of y equals cosine of x, which is right there. And of course, just as with sine of x, y equals sine of x, this is a periodic function, so it's definitely not one-to-one. So if we take the line y equals x and then reflect this over the line y equals x, what's it going to look like? Well, it's going to look like that, and that is x equals cosine of y, which is clearly not a function. So we want the inverse cosine function to be a function. So it can't be a reflection of the entire y equals cosine x. So what we need to do is we need to take a smaller piece. And we want to take a piece that certainly includes what corresponds to an acute angle in the unit circle picture. So we're going to include this part from 0 to pi over 2. But then we want to also include something that takes care of the negatives. And if you look, if we just continue on from 0 to pi and look at that for our restricted version there, then this will be an inverse, or this will be the part that we want to find the inverse of. And so this is the cosine of x. It's that function, okay, but it is restricted to this interval from 0 to pi. So we basically erase the rest of the cosine of x. And when we take that and reflect it over the line y equals x, that gives us the Arccosine, or inverse cosine function. Notice it is a piece of the more general function, more general relation, I should say, of x equals cosine y, which is not a function. It fails the vertical line test. But if we keep this part, with the purple part we have here is the y equals cosine x for x from 0 to pi, and that is a one-to-one function. So it has an inverse, which is also a one-to-one function, and that's what you see in green here. And you can see that those two are mirror images of each other over the line y equals x. So if we get rid of everything except for the actual Arccosine function, this is the function that we have right here. Let's put some reference lines in there to kind of help us see things, and maybe zoom in just a tad. Okay, and what do we see here? Well, our reference lines, this one at the top is y equals pi. This is y equals pi over 2, and of course we get y equals 0 is the x-axis here. And we see this is -1 for x, and this is +1 for x. So we see it's in this box right here, completely contained in that. And then what are the corners, opposite corners of that box? Well, this one right here is going to be -1 comma pi, okay, which is one of the endpoints, -1 pi, and 1, 0 right here, the one that says scale, that is the other endpoint. So what's the domain? The domain of Arccosine is the same as the range of cosine, which is -1 to 1. So notice when we did the restriction, okay, and we went back and we did this restricted version of cosine, notice we did not change the range. So we still kept every y value, but we just only kept them once. So we got rid of a whole bunch of points, most of the graph in fact, and so that we only kept not even really a full period. Actually, we only kept half of a period of the cosine wave, and that's what we found. That's what we flipped over to get the Arccosine. So let's look at some properties that the Arccosine has. Okay, our inverse cosine. The domain is -1 to 1. The range is 0 to pi. So the output is 0 to pi. And you can also think of the output not in this picture, which of course the output here is a y value, but you can think of the output as an angle. And what kind of angle do you get? You get an angle between 0 and pi inclusive. So basically acute angle, right angle, a obtuse angle, or straight angle, or zero angle, angles that you could get inside of a triangle, and also a straight angle and zero angle. Okay? Notice that all of these inverse trigonometric functions include an outputs between 0 and pi over 2. So they include, in this picture over here on the unit circle, they include outputs that correspond to angles that are acute angles. And notice we actually use the inverse sine and cosine, and inverse sine, inverse cosine, and inverse tangent functions when we were solving right triangles. We already used them, but we were only doing them for positive inputs. So if you take a positive input, which is a cosine value that's positive, notice that your output will be an acute angle. But when you input a negative here, the output is an obtuse angle. Okay? This particular one is a continuous function, meaning it's all in one connected piece. It's decreasing the whole way, and so that makes it a one-to-one function. It does have an inflection point, which is also the same as the y-intercept, and that happens at 0, pi over 2 right here in the middle. It has endpoints starting up here at -1, pi, and then it goes to -1 or +1, 0. Those are the endpoints. Of course, 1, 0 is also the only x-intercept. And it's an inflection point here on the y-axis, so this part in the third quadrant right here, x is going from -1 to 0, that's where the graph is concave up, and then it switches to concave down in this part right here, from 0 to 1. And that is a pretty good overview of the arccosine. One final thing, just as with sine, we have different notations. The most common way is y equals arccosine of x, or cosine superscript -1 of x. And so we would pronounce that, this one we'd still pronounce either as arccosine or inverse cosine. You could also see INV COS or A COS. Graphmatica uses a cosine of x, that last one, but most of the time we'll see one of these first two. Again, I really prefer arccosine of x so that you don't get this confused with an exponent, but most of the time I guess you'll probably see this one as much as anything, because that's the notation that you have on your calculator screen. Speaking of calculators, let's pull up a calculator here, and use our cosine with our calculator a bit. So first of all, when we're doing these graphing, we want to be in radian mode, which I am, and I can graph this one as the inverse cosine of x, and we'll start with a zoom standard. Okay, and there's the graph. Maybe we want to zoom in a bit. Actually, what would be a decent window? Well, it's really all between -1 and 1. Let's go a little further, -1.1 to 1.1 on x. And what's the y? Where do the y's run? They run from 0 to pi. Let's go a little bit in the negatives. Let's say -0.1, and pi is about 3.14 something. Let's go up to like 3.2 or let's say about 3.3. And maybe we'll mark both x and y off in 0.1 each. Actually, it'd be better to mark y off in some multiple of pi, like maybe mark it off in like pi over 4 or something like that. So we'd have a trig scale going up on the vertical axis. And so we can graph that. course, that should agree with this green graph. It's the green graph over here is actually on a square scale. This one's kind of stretched out a little bit more in one direction than the other on the scale. So there's the arccosine. You can look at values of it by, of course, just looking at your table. So let's actually start it at -1, and we could go up by pi over 12 or something, maybe, automatically. And then take a look at our table. And of course, actually pi over 12 is not a good thing to go up by. Let's, well, that's okay, but let's go, we'd probably be better just to go up by like 0.1 or something. And you can see that -1, that's pi, approximation of it, and you can get some output values here. Now these output values are actually angles in radians, and of course we get error messages once we go beyond 1 or outside of the interval from -1 to 1. So we can evaluate that, and so if I say inverse cosine of 0.25, what am I saying? I'm saying give me an angle whose cosine is 0.25, but not any angle. What angle specifically? Specifically an angle in radians, because I'm in radian mode, between 0 and pi. So give me an angle between 0 and pi whose cosine is 0.25, and that's what the inverse cosine gives you. Now if you switch mode to degree mode, then we wouldn't want to do this for the graph, but if I did the same thing, now it's going to give me that same angle in degrees. So now that we're in degree mode, this is the output is an angle in degrees between 0 degrees and 180 degrees inclusive, whose cosine is 0.25. So I'd rather go back to radians here, so let's go back to radians. And so if we do the inverse cosine of a negative number, now of course what if I put in -2? Well, we're going to get an error message. Why? It's a domain problem. Okay? The only thing that's acceptable for an input is something between -1 and 1, because the input has to be a value of cosine. The output value, the input for an inverse cosine is an output value for cosine. So it has to be between -1 and 1. But say if I put in -0.5, for example, I'm saying give me an angle whose cosine is -0.5, and actually you should probably know what this one is, I think. Let's see. Let's kind of draw a picture. We know we're talking about an angle between 0 and pi, and that cosine is negative, so it's going out this way. And we know the cosine is x over r, so it's 1/2. That's not drawn to scale. It should be more like if this is we could use a circular radius 2. If that's 1/2 like that, we know that's square root of 3, and we know this reference angle is pi over 6. So the angle that we're looking for is this one, which is 5 pi over 6. So if I do 5 pi over 6, not the same. So what am I? Oh, pi over, I'm sorry, this one's pi over 3. Excuse me. This is the bigger angle. This one up here is pi over 6. This is the bigger angle, 60 degrees. So that's just pi minus, this is 2 pi over 3 is the angle we're looking for. Let's try that, see if that's better. 2 pi over 3. Yep, that's it. Which, of course, if we did that if we multiply by 180 degrees and divide by pi, we'll get that as 120 degrees. Okay? So again, the inverse cosine or arc cosine is going to, if you want to think of it in terms of, which we usually do want to think of it in terms of a unit circle picture, the output is going to be an angle, and it's going to be an angle between 0 and pi, whose cosine is whatever you have for the input. So that's basically how the arc cosine function works.